Welcome, Stefan, for coming and giving us a very nice talk today. He did his grad work at the Max Planck Institute, followed by a postdoc at Fermilab, working on a very ADMX, and now he has joined the faculty at Harvard as of this January, working on a couple of Axion experiments that he'll go into in his talk. And with that, take it away.
Thank you very much. That was a very nice introduction. Thank you for this invitation. This is really a pleasure to be here. I saw already this morning you have quite a few fun experiments. I'm looking forward to seeing more this afternoon. So as you said, I'm going to tell you about quite a range of Axion searches for what we call the high mass range for Axions, which is actually still relatively low mass compared to other particle physics ranges. I saw you had a bunch of talks about Axions already in the last couple of months, weeks. So the first 10 minutes, if it's going too slow, just let me know and I can speed up. But later we're going to talk about some of the GigaBREAD and ADMX stuff, which is new. So all right, without further ado, why are we doing all this? I'm an experimentalist, so I have this naive picture of a neutron, where the neutron is another fundamental particle. It consists out of an up quark and two down quarks. They are charged, and so they have some separation. We know roughly how big that is. So if you look at this, you would say, oh, this thing clearly has an electric dipole moment, right? There's more negative charge on one end than on the other, and you can estimate this. And when you go to the lab and you try to measure it, and what you'll find is you don't see any dipole moment. In fact, the dipole moment constraints that you set from your zero measurement are 10 orders of magnitude more stringent, or even more than that, than this naive estimate. So what's going on? Well, you go to your theory colleagues and say, okay, why is this happening? And they say, yeah, okay, this dipole moment is actually predicted through this theta term in QCD. This is the only term that actually gives you this dipole moment, and it would break CP, and it's regulated by this constant called theta, which is in front of this GG dual term, and it's an angle. And okay, if it's an angle, you would expect it to be order 1, and if it's order 1, you actually end up pretty much with a dipole moment which is around the order of magnitude that we just estimated on the previous slide. So the angle, more or less how these neutrons, these quarks are aligned in the neutron, is exactly pretty close to 0, actually 10 to the minus 10. So that's possible, but seems very unnatural. Nature just chose this to be exactly 0. So the solution that has been proposed about 50 years ago is, oh, maybe there's a field that compensates with theta and undergoes spontaneous symmetry breaking in the early universe with a potential that is naturally minimized at 0. So you can start out at any theta value, but as the universe expands, the energy density in this field can dilute, and the field oscillates. And as the universe expands, these oscillations just get dampened out around the minimum and naturally sit at 10 to the minus 10 around 0 nowadays. And of course, these oscillations amount to an energy density in the universe. In particular, this is a new massive field. It corresponds to a new massive particle, of course, the Axion, and therefore give you a very nice dark matter candidate as well. So that's the motivation for the Axion in a nutshell. And of course, we want to search it. So where do we want to search it? This is the parameter space people usually look at when they search for Axion. Right. So on the vertical axis, you have the coupling of the Axions or dark matter to something you know. In the case of Axions, it's the coupling to photons, as you're aware. And on the horizontal axis, it's the mass. And what's really striking about this plot is just its vastness, right? You see there are orders of magnitude, 10, 20 orders of magnitude on the horizontal axis that we still haven't really probed. And we could give lectures about this plot. There's really rich physics in all these constraints that go in here. But today I want to focus on two things. One are these laboratory experiments which go down here, which are the ones, or some of them I'm involved in, some of them you are already involved in. And these are really the only kind of laboratory experiments that go down to this yellow band, which are the benchmark QCD Axion models, which would solve the strong CP problem. The other wide range are Axion-like particles, which behave like Axions, but actually don't necessarily solve the strong CP. Okay, so this is where we want to search. And obviously there's a coupling with photons. So how can we use the coupling with photons to search for axions? Well, that goes back, of course, to the interaction between the axions and the photons. And again, if you ask the theory colleagues, they will write down this Lagrangian. But it turns out that because axions are so light, like microelectron volts, they are actually so abundant in the local density that they behave like a classical field. And this classical field actually just modifies Maxwell's equations. And because there's this interaction with a FU dual, which in particle physics, Feynman graph is just an interaction with two photons. If you assume you have a strong external magnetic field, your strong external magnetic field induces source terms to your Maxwell equation. And these source terms behave like charge densities and current densities. So really 90% of the experimental efforts that search for axions with the photon coupling, they basically just try to leverage these source terms. And if you squeeze your eyes even closer, you can see that on the one hand side, you typically have a derivative of the axion field. And on the other side, you have a derivative of the electric field. So in very simple terms, you can say, okay, if I have this external magnetic field, apply a strong magnetic field, then what I get is an axion-induced electric field through these source terms that's proportional to the axion. So that's what's written in the last line. I have an electric field that's proportional to the magnetic field and the axion. Of course, it would be nice to detect that. Unfortunately, it's extremely tiny, 10 to the minus 12 volts per meter, even if I have a 10 Tesla magnet, which is around the order of magnitude of some of the strongest magnets we have. So that's quite challenging, but there's one nice thing. The axion field, like we said at the beginning, is oscillating in time, and is oscillating with a frequency that corresponds to the mass of the axion. So if we can leverage this oscillation, maybe we can detect this. Okay, if these are all too many equations, we can draw a picture. I apply a strong external magnetic field, right? And then if axions are around, what will the axions do? They will interact with the magnetic field, they will mix with the photon and introduce an axion-induced electric field, which is proportional to the magnetic field, the axion field, and a time oscillation that is proportional to the frequency, to the mass of the axion. All right, so this is very tiny, hard to detect. But now if I put a resonator inside this situation, I can resonantly enhance this axion-induced electric field inside the resonator by the quality factor of the resonance and get the electric field to a level where I can actually detect. This is an idea that's about 40 years old, introduced first by Pierre Sikivi, who recently retired at the University of Florida. And then, okay, what do? You put an antenna in here, you read the signal out with a low noise amplifier, like Case-Like is doing, of course. And then you look for a signal that appears at a frequency corresponding to the axion. This is, of course, just a cartoonish picture. In ADMX, this is how our setup looks like. So down here is our magnet. This is about the size of the cavity. It's still the shield around, but you can see the cavity is about 1 meter tall, about 50 centimeter in diameter. And this is just as we pull it out of a wet fridge. On the other side, this is when it's inside, it's looking from 180-degree different perspective and all the readout electronics behind. So this is not a tabletop experiment anymore, but also not a crazy particle physics experiment yet. I won't spend too much time on this because most people are familiar with this, but just to give you an impression what all this entails, of course, this large superconducting magnet, really not an MRI magnet, not much interesting physics, just a large expensive thing. The resonator, again, about 1 meter tall cavities with tuning rods. The most recent one actually only has one tuning rod to go to a little bit higher frequencies. But that's what we're doing. We have these copper tuning rods in there, which we rotate from the outside to the inside. So we can change the resonant frequency of the cavities in order to probe different axion masses. And then, of course, we connect it to a low noise receiver chain. In our case, those are some parametric amplifiers, pretty much similar to what Haystack is doing as well, to read out signals. And then, I could give a talk about the data analysis, but essentially you end up with a result which looks like this, right? You constrain the axion down to, of course, the QCD axion model band, and with our setup. And it essentially just looks very noisy because what you're picking up is noise. And if you're more lucky, your sensitivity is better. And if you're less lucky, that's what the noise fluctuates up. Yeah, if you just want the most recent update from ADMX, just follow this link to our most recent paper. So maybe what's a bit more interesting is where do we want to take ADMX in the future? So right now, this is pretty much where we are. We actually have some newer results, but more or less this is the whole range. But we want to double this range. So we want to go to higher frequencies because, okay, if the pre-inflationary axion model is true, then we don't really know where the mass of the axion, where the frequency should be. But there are lots of predictions that point towards higher masses. So in ADMX Gen 2, which is the slate of runs that's currently going on, we are probing this range and in EFR, again, a factor of 2 in frequency increase. So what's the game about this? Well, this is a lambda half resonator, more or less, right? So half a wavelength fits inside this cavity. So if you want to go to higher frequencies, and we are talking about orders of magnitude are unprobed, or maybe just an octave or ADMX, what that means is the frequency goes up by some factor, which means the size of the cavity goes down. So the cavity gets smaller, which means the volume of the cavity goes down, which is a problem because your signal goes with the volume. And well, the easy way out is, of course, why don't we use many cavities and combine their signals? In fact, the signal of each individual cavity is coherent. So you can coherently combine them if you can keep track of the phase and get back to the same volume. That's the idea in ADMX, and the ADMX EFR, for example, will have 18 cavities like this in a new magnet at Fermilab, which goes up to 9.4 Tesla. And we think that with this larger volume and larger magnetic field, we can scan with the FSX sensitivity the 2 to 4 gigahertz range in about a scan time of 3 years, which is significantly faster than what we have done with the current ADMX bands, just because we have more volume here. The resonators will have their dedicated dilution refrigerator, and the readout electrons will be far away from the magnetic field to shield them, and each individual cavity will have their own readout electron exchange. So that's of course cool, but that just gives us 1 or 2 orders of magnitude in mass. So if we go back to that plot, we are here, and then we multi-tier runs, painstakingly go to maybe something like here. But really the predictions of the theorists where the post-inflationary symmetry breaking axion will be is around there. So that's still like 4, 5, 6 orders of magnitude that we have to probe. So easy. We just, instead of 18 cavities, we build 1 million cavities and combine all these 1 million cavities together, tune them together, combine them. Well, obviously this becomes really, really very complex. Even if you can do it, you have to tune all these cavities in sync to phase map them. So to go orders of magnitude higher, the cavity concept is just not feasible anymore. So what can we do instead? Well, if you look at this cartoon, the only thing that really makes us the most headache is the resonator, right? We know how to get big magnetic fields, And we actually also pretty much know how to get quantum limited sensors or even better in various frequency ranges. So let's be radical. Let's get rid of the resonator. Let's do something better. In fact, if you have a sensor that's so good that you are background free, the resonance doesn't help you anything actually. So what does it mean not having any resonance? Well, it's basically having a quality factor of 1. That's like, take your cavity, take all the balls away, except one ball, and look at the signal coming from the ball. Now, why does that make sense? Well, let's go back to our initial picture with the external magnetic field. What does the external magnetic field do? It induces an Axion-induced electric field, which is tiny, but which oscillates with a frequency corresponding to the Axion mass. Now, this is a tiny field, but in this metal slab, I have electrons. The electrons see this Axion-induced electric field, and they will try to follow it. They will try to compensate for this force that's acting on them. So I have electrons that move in a metal slab. Well, that's an antenna. That's why this is called a dish antenna. And an antenna emits electromagnetic radiation, right? So now I have this plane wave emitted from this slab, non-resonant. It's just a propagating wave away from this slab. This happens at any frequency, regardless of the geometry of the slab, which is nice. And I can make the slab much, much bigger than the wavelength. Which is unlike the cavity, which has to be matched in size to the cavity. And then I just, kind of take it to a geometry where I focus all these plane waves onto a focal spot. And by making this thing large, get a large signal back. This is a nice concept. It has been kind of proposed around 10 years ago. The only thing that has given people headaches is, well, you need a magnetic field which is parallel to the surface of this emitter everywhere on the surface. And the natural shape for the surface is, okay, a half sphere, because then all these photons are focused on the center of the sphere. Now, I've given this talk at Fermilab before, and said, well, it's basically impossible to build such a magnet. And then one of our magnet builders stood up, hey, wait, I know how to build this magnet. How many $1 billion do you give me? And then I said, I don't have billions or billions of dollars. We need something more cheap. And so what's something more cheap? Well, it's a kind of magnet we are all using every day, maybe already, which are just solenoid magnets. So we came up with this concept that makes a dish antenna compatible with a solenoid magnet. So as the emission surface, you use a cylinder instead of a half. Okay? So all these photons are emitted perpendicular from the cylindrical ball, which now is parallel to the direction of the magnetic field in a solenoid magnet. And then we put focusing optics inside to collect the photons. And in our case, this is this parabolic tip reflector, which is this parabola revolved around its vertex tangent. And so all these photons get emitted, get reflected once on the parabola, and then reflected again on the outer cylinder, and be focused on the focal spot at one end of the solenoid magnet, which is perfect because they can put your readout chain again and shield it more nicely from external magnetic fields. So we had this idea, we did some sensitivity estimates for it. We thought, okay, we did some more realistic sensitivity estimates. We have this new shape, but really this has been proposed more than 10 years ago. So which journal should we put this? We add something to this discussion. Well, let's try PRL. And we ended up on the cover page of PRL, which I think is really cool because it shows that there really is a lot of hunger in the field to actually find methods to access this high frequency range for Axion searches, which are not accessible with the cavity method. So we did a bunch of sensitivity estimates for various sensors out there, kinetic inductance detectors, transition edge sensors, quantum capacitance detectors, SMSPDs. And you can see that with some optimism in R&D, and for large-scale 10 square meter bread in a 10 Tesla magnetic field, you actually have the potential to eventually reach the QCD Axion model band. So this is, of course, quite encouraging. And of course, we were not just happy with this concept paper, we wanted to actually do this. So one prototype which is going on right now actually is the infrared prototype, and these prefixes already tell you what the frequency range is. So this is BREAD with an SNOSPD, superconducting nanowire single photon detector, where you detect infrared photons with a nanowire and the focus, and combine this thing with an optically smooth BREAD detector. Since this is something going on, we are just assembling the big reflector. There are not a lot of results to show yet. So this is all I'm going to show you for infrared for this. But this is to give you a flavor of how broadband the BREAD concept really is, because this is infrared, very far away, orders of magnitude away from where, for example, ADMX is searching, and orders of magnitude away from where our GigaBREAD prototype operates. So this is me sending beside kind of my BREAD prototype that I built a couple of years ago, which is a meter scale 10 gigahertz detector. So 10 gigahertz is like centimeter wavelengths, right? But this is still orders of magnitude larger than the wavelength. You have this outer cylinder, which we use as a conversion surface, and this inner parabolic reflector, which then focuses all these photons. The first thing we, of course, did for this was a lot of simulation and modeling. We designed a custom horn antenna that goes in the focus to pick up this radiation that's arriving here from the side. And we understood, the electromagnetic response of the setup as good as we could. I think we did it more than other like prototype dish antenna experiments are doing, because we can actually get some standing waves between this antenna and the surface you're looking at, the mirror, which modifies its sensitivity. So what you see on this plot is on the horizontal axis, you have frequency, and on the vertical axis, you have position of this antenna. So if you move the antenna out of focus, then of course you lose your sensitivity because you're out of focus. That's not where your photons are being focused anymore. But if you move the antenna in the focus, you see this pattern of weak resonances appearing, which are the standing waves between your antenna and your outer wall. So it's not completely flat. You have still this combo of weak resonances, but you can kind of, by wiggling this antenna around, you can make it. That's what we do. But we try to verify these simulations by measurements. So one of the measurements we, for example, did is we measured the thermal noise that's coming from the setup, just at room temperature. And what you see is exactly the same spectrum. So if you are on focus, your antenna looks at the mirror. The mirror is electrically cold. So the noise that's coming from the reflector on focus is minimized on average, whereas when you move the antenna away, you get a large amount of noise. And of course, you see the same kind of resonance structure, because on resonance, again, the setup is expected to absorb more photons and again, behave more like a bypass. So these spectra are of course not the same, but they are correlated and they can confirm that your understanding of the electromagnetic properties of the system are correct.
What resonance are you talking about here? I thought this was a non-resonant.
I mean,
You just mean
the net of these standing waves is like one, right? So it's not really resonant, but it's, if there is a small reflection coefficient on your antenna, it still means that part of the coherent photon ray function is being reflected, and in the worst case can cancel out some of your signal.
It's like a standing wave between the
Exactly.
antenna and
Yes.
the
It's a mismatch, right? And every antenna has a mismatch. So it's important to take it into account. You can do something about it if you want to be completely non-resonant. You move this antenna in this range up and down periodically while you're taking data, and you just average everything. We analyze the data a bit better than that. If we don't have sensitivity in the frequency band at a given position, we weight that data less than when we have higher sensitivity. Yeah. Okay, so that's the reflector. The other thing you need is a broadband data acquisition. So for a cavity, all you really care about is about a narrow frequency range, which you tune around. But in BREAD, we wanted something as broadband as possible. And at this stage, BREAD is a small R&D experiment, so we didn't have a ton of money, but we wanted to make it as broadband as possible, say 20% instantaneous bandwidth at 10 gigahertz, which means if you want to save all the time series of your data, you need to acquire 4 gigasamples per second, or in other words, at least save 8 gigabytes per second of data. That's obviously a lot of data, and you need some real-time data reduction scheme, which we developed with Fermilab engineers on the Xilinx ZC111 FPGA board. So the idea here is that we take data in parallel with this body-phase filter, take the 4 gigasample ADC of the board, calculate the FFTs in parallel, and then square them and add up the power spectra in the memory of the FPGA board. And all you save is an average power spectrum roughly every second. Like all the transient effects of Axions or dark photons that we're interested in, they would happen typically at longer timescales than that. So 1 second is really very reasonable, and that is enough to reduce your data throughput by a factor of 10,000 and makes it very reasonable to handle with just a standard computer and relatively low cost. So we have a negligible dead time, even though we are acquiring a 2 gigahertz instantaneous bandwidth. So we built an experiment. This is how the first experiment looked like in 2023. To make sure we get rid of all the backgrounds, we used this electromagnetically shielded room at the University of Chicago. Just imagine Wi-Fi or some other communication signals are right in this band, or at least below this band. We put it in this shielded room. This is the reflector again with the antenna, which we can move up and down, connected to a low noise receiver chain, which adds about 100 Kelvin of system noise. So we did this experiment, and actually the shielding was really good. We took data, and this is how the result looked like. And you say maybe shielding is not so good, because this is the excess noise. The dotted line is the 3 sigma global threshold, and oh, wait, we see 2 signals. Anyone have an idea what those 2 signals could be?
Axions.
That would be really great, no? Well, this is another thing which we did maybe for dish antennas for the first time. For cavities, it's pretty standard. We injected test signals. So these 2 only peaks that we see with a high global significance are test signals we injected ourselves. So I had my grad student choose 2 random frequencies that I didn't know of, taped it off on the signal generator, literally. So, and we had this pin antenna right underneath the wall of the reflector. I took a picture underneath the wall, but kind of hard to see, but this is just the pin antenna itself. And injected those signals for 2 different data taking periods at 2 different frequencies. And while they appear in the spectrum, roughly at the, well, not roughly, exactly at the right frequencies and exactly at the right times when we inject it. So this is cool. The other cool thing is I told you about this resonant kind of modification of the response. These injected signals, of course, undergo the exact same effect. So if I move the antenna up and down, we kind of try to resolve how the injected signal behaves with the antenna position. You can see that the data exactly behaves like we would expect from a previous network analyzer measurement. So this is nice. I think this shows we can see signals that actually come from the reflector, and we understand the reflector response. So unfortunately, we haven't seen any signals. So all we did is we set constraints on the dark photon parameter space, because we also didn't have the magnet yet. And you see, okay, it's fairly broadband, 20% bandwidth at this 10 gigahertz range, which is relatively high frequency, but there are other broadband limits from other dish antenna prototypes out there these days. But But what is our advantage is really this compatibility with the magnetic field for a solid light magnet. So what we did this year is we adapted this whole setup. Actually, we didn't adapt it much. We just put this whole setup in a 4 Tesla MRI magnet at Argonne National Lab, which you can see here. So it fits beautifully exactly in this magnet. And you might know this gentleman. I think he has worked here before. One of the best graduate students I ever worked with, Gabe, because he did all this work while I was applying for faculty positions. I didn't really have time for this. So lots of credit go to him. You see, now we don't have an electromagnetically shielded room. So we had to do a lot of work to kind of have a rejection data taking chain and a lot of absorbers around the setup to make sure that we don't get all these Wi-Fi signals into our chain, which in the end worked actually quite well, but was some effort. And now we have the first result. We are just about finishing writing up the paper on it. So this is the result which we got. It's slightly better than the CUST limit, which is, I think, for such a small R&D experiment, really, really nice. Has the same 20% bandwidth, and is the most sensitive laboratory experiment in that range. It's also the first dish antenna experiment among all the other dish antennas that are out there, which sets constraints on axion-like particles. I think that's really cool. Of course, this is just about the CUST limit. It's not cryogenic yet. It's only quote unquote a 4 Tesla magnetic field. So the immediate plan is to just upgrade this with the larger Fermilab magnet, for example, or a cryogenic environment to immediately improve the sensitivity by something like an order of magnitude. But these are just pilot experiments, first R&D. What we really want to do in the long run is we want to do this, right? So let's look carefully at this plot. So what did we assume here for these dashed lines? Well, we assumed that these sensors still improve by a factor of 100 in terms of noise equivalent power in the next couple of years, which is not crazy. But also it means that for the single photon counters, their dark count rates have to improve by 4 orders of magnitude. So depending on the sensor, this could be optimistic. And then if you look at these dashed lines, you see, yeah, they go into the QCD Axion range, but there's actually only a small range around here, maybe with the SMSPGs at very high frequencies, where we go down to the DFSZ model. And all these theorists tell us, oh, it would be better if you even search 1 or 2 magnitudes below the DFSZ model. So we clearly have to do better than that, not only on the sensor side. So this is the other thing I'm excited about, and I'm going to work hard at Harvard to advance. So one idea improving the dish antenna is, well, why just use one dish antenna? You can do something like a stack of dielectrics, where now each of these dielectrics behaves something like a dish antenna, and add up the signals from all these dielectrics together. This is a beautiful idea because dielectrics are electrically transparent. The only issue is, of course, this is a coherent emission. So what you get is a coherent summation of all the contributions from these disks, and actually something like the weak resonator again. We have a prototype of this. Actually, this was kind of my PhD thesis, MADMAX. So we do this in a similar frequency range than GigaBREAD. And I brought the data acquisition system that we built for BREAD. Last year, I brought it to Germany to take data with this particular prototype to get first data with something like this. And actually, we just put out the paper on this, and we get similar results that you just saw on GigaBREAD. So this is really nice. So this is one way of getting higher signal. The other idea which we have is, okay, we are still far away from being background. So you can actually win by adding resonance back to the BREAD setup. Now, you don't want to build millions of resonators, but the other idea is just to use a higher order resonance in the BREAD reflector. So if you put a mirror instead of an antenna on the focal spot, what will happen is your photons will bounce between the outer wall and the mirror on the focal spot, much in the way like we saw for GigaBREAD with the combo of resonances. But instead of not having them resonant at all, you can tune your setup in a way that they are as resonant as you can get them. And then you just tune this comb from one mode to the other end again by moving sort of your mirror on focus. And again, some broadband sensitivity because we have this broadband comb with minimal tuning. So we had this LDRD proposal, which I wrote last year, which got funded, which is really cool. So we are building this prototype right now. And the idea is in the long term to put it in my magnet at Harvard University and do a first run in the millimeter wave range with this prototype. And what you can see is that even for such a small prototype in a 9 Tesla field, this enables you to go below the astrophysical bounds in the millimeter wave range, which is quite something, and no one really is trying to do this at the moment. And would potentially be the first terabit Axion search experiment out there, which I think will be really cool. Again, this just barely competes with the cast and astrophysical bounds. So in the long term, we have to scale all this up. So whether it's dielectrics, resonances, or some combination, this is only the first step. Essentially, once that works, we know what we have to do to scale it up, to make it large, to use more layers, or to use, better resonances, eventually going down to the QCD Axion model band. And here, this estimate, you see, okay, it's a large-scale BREAD with a large-scale reflector in a large-scale magnet, but even just with a quantum-limited amplifier, you might be able to do it in the millimeter wave range. But what it really shows you is you still need a large-scale facility of doing this. So this is the other thing we are actively working towards. So we are working with various collaborators to make this platform, which is the start for ADMX EFR that I just have introduced a couple of slides ago, into a platform for a set of experiments that can be this intermediate step to a larger scale program for Axion searches. So for example, a large scale version of BREAD could already go as a side experiment to ADMX EFR. This magnet is there, it's just not ramped up yet. So last year this arrived at Fermilab, and we have this experimental hall where it's currently being installed and this year being ramped up. So this is really exciting. So this is most of the things I wanted to tell you about today, actually. So at the end, I should thank all the collaborations I'm part of. So ADMX, of course, MADMAX, and BREAD. And hopefully by the time I retire, this plot that I showed you fix at least something like this, maybe even more parameter space is covered, or we have to cover something. That would be, of course, even nicer. So thank you for your attention, and I'm looking forward to your questions.
All right, thank you for that wonderful talk. We have time for some questions.
So in the non-resonant traditional BREAD or something.
Yeah.
So you're like losing factor of 10,000 or something from having no Q, and then you're like scaling the area very large. Yeah. So some part of it is you have much bigger area, then some part of it is you're getting this like single photon counting limit.
Yes.
Do you have a sense when you're putting those projections, like what fraction of the sensitivity is recovered from, or scan rate or whatever is recovered from, like moving to the quantum sensors or from the area?
It's always a combination, right? But it depends a lot on the frequency range because the sensors vary a lot by frequency range. Yes, and SPDs, they have dark count rates as low as 1 photon per day. So at the high frequency end, it's relatively easy to go down to the QCD Axion model band, whereas in between, it's kind of hard still. That's why we are so interested in millimeter waves with these additions, right, the dielectrics. yeah, I mean, all of this is R&D, so I can't really tell you where this in the end, how they will balance. I think we will need large scale, we need large signal, and we need the best possible sensitivity all three.
Yeah, so I guess on the sensor side, you're talking in any piece. I guess you're assuming like a diffraction limited spot and you're getting, because if you get all that power into a smaller sensor.
Yeah, this is a very interesting topic that I completely glossed over in this talk. So there are two regimes in the sort of until about 500 gigahertz. The radiation in your reflector is completely coherent. So the Axion wavelength, the broadly reckoned, is about 1,000 times larger than the photon wavelength. So the radiation that's coming from your fan is coherent if your photon wavelength is not much smaller than a millimeter, because if you're talking about meters. And in that limit, you get a diffraction limited focus at a zinc point. If you go above that, you get phase differences over the emitter. And these phase differences mean that at different times during your data taking, that focus moves a little bit around the focus. And it smears it out on the scale of a millimeter, no matter what you do. So in the optical range, you have a millimeter size focal spot that's still 1 millimeter and is completely incoherent. Nothing you can do about it. But the SNSPDs, for example, are incoherent detectors, which today have about that size. So that's a nice fit.
Okay,
but
so
yeah.
you can do drastically better by some tricks because you always have this like.
Yeah, so so in the regime where it's incoherent, you can play some tricks. I don't think you can get drastically better, but if you say, okay, this must be a dark matter, and it must have like a dark matter momentum distribution, what you could do is you could have a pixelated detector with much smaller pixels than a millimeter size, and try to resolve this movement of your focal spot. Once we see a signal, we break it down in sub timestamps and then see whether that corresponds, for example, to the rotation of your setup in with respect to the dark matter wind. And if it does, then it would be a very clear signature of a dark matter signal, right?
That's all that's one more.
Yeah.
Well, you have this nice electronics, so you don't have to digitize continuously, but if you get bursts that you have to throw out, I mean, is a second and good enough integration time that you're not throwing out quantities of everything because you have some transient noise? Is that just not there in this frequency range?
I don't think we have any unexpected noise that would be on a shorter time scale. At least the noise that we do, that seems to be the thermal noise that we expect. I'm not really aware of models that produce very short bursts.
I mean, I assume like cell phones and Wi-Fi.
Oh, yeah, sure. But I guess we are shielded well enough against them. And actually, yeah, it would help to discriminate them if it's less than a second, right? Yeah, so far we haven't seen any signals that impede us. What we have in the GigaBREAD at the Magnet Argonne National Lab, because there's actually an accelerator, an RF accelerator right besides, we did have to do active vetoes. So we had a second data acquisition chain, which mirrored the one that is taking data, but with an outside antenna. And whenever that antenna saw a peak in a certain frequency range, we just shut off the other chain in exactly that range and vetoed those signals, and that just vetoed everything away that we were worried about.
If we don't have any questions at the moment, could we thank the speaker one more time?